Hi everyone, welcome to Modern Optimization Methods. Today we will introduce the second part of Chapter 2, which is the Wolf conditions. Now, let's first recall the line search strategy. As we mentioned before, the line search strategy actually takes two steps. So at the current iteration, we need to first choose a direction, which is a descent direction, and then we determine a step length alpha. Then we move to that iteration. And the question is, how can we choose a reasonably good step length alpha k? So as we demonstrated in the previous lecture, choosing an important inexact step length is very essential. So the idea is how we can find sufficient decrease condition to guarantee the convergence of f to the local minimizer. Now, let's first introduce the first condition in Wolf condition, which is the sufficient decrease condition. So the sufficient decrease condition is illustrated by this inequality here. So if we look at this inequality, the left-hand side basically says the next iteration, okay? The function value of next iteration. And the right-hand side actually is a sum of two terms. The first term is the current function values, fxk. And the second term is we use the inner product of gradient f at xk multiplied by the direction pk. Then we have some constant here, c1 multiplied by alpha. This constant actually controls somehow the step length. Okay, so notice that the second term here, it is a negative term. So it guarantees that the next iteration is strictly smaller than the current one. And now, what does this inequality mean? It actually means that the reduction in function f should be proportional between the step length and the directional derivative reduction this term. Okay? So now let's illustrate it geometrically by a figure. Before we present the figure, let's first do some reformulation. Okay? So what is the reformulation? So we transfer this inequality in terms of phi alpha as well as a line. Okay? Now, let's recall that phi alpha here, it is a function of the step length. And if we take the step length at 0, then we are standing at the current iteration fxk, which is phi 0 actually is the same as fxk. And similarly, phi alpha k is actually the next iteration fxk. Now, if we do the gradient of phi with respect to alpha, then we use the chain rule. We can get that phi prime at 0 point takes this value here, which is exact the gradient of f transpose pk, okay? So this term is actually the tangent of the function phi at 0 point. So try to remember this, keep it in mind. And now for the phi prime alpha k for general alpha, we have the iteration like this. So phi prime alpha k is calculated by the function values of f at next iteration multiplied by pk, okay? So this is about the left-hand side, f xk plus alpha pk. This is the second left-hand side. We transfer it into phi alpha. And for the right-hand side, if we take it as a function of alpha, it is actually a linear function, all right? So for this linear function, we denote it as L, and L alpha is the right-hand side. For the coefficient of L alpha, it is actually, we call it the slope. The slope of alpha is actually take this value multiplied by C1, okay? So it is also -1. However, the slope of L alpha is a little bit different from the slope of phi alpha because they have a ratio relationship, right? So now, after presenting these relations, we transfer the conditions to this one. So we actually require that for the phi alpha, this curve, it must lie between this line, L alpha. So this is the figure we want to illustrate. And we still have the function curve about phi alpha here. And then we plot out the straight line L alpha in dotted. So you can see that if we try to find the part that phi alpha lies between L alpha, then this is an interval which we can accept. And this is an interval that we can accept. So the two intervals actually returns us the acceptable step length. So actually there are quite an amount of step lengths that can satisfy the first condition. All right? However, you may notice that there is an interval which is very close to 0. They are also acceptable. So in a very bad situation, if we choose this alpha very close to this 0, then it satisfies the sufficient decrease condition. However, in practice update, it means that we can only move forward a little bit, okay, just like this. So it will slow down the iteration process. Therefore, the next condition in Wolf conditions will rule out such small size of alpha. All right? And then we come to the second condition called the curvature condition. And this condition actually, in mathematical form, it presented like this. Okay? So we recall some gradient at next iteration, transpose pk is greater than or equal to a constant ratio of the current iteration multiplied by pk. So similarly, if we transfer this condition into the form of phi, then we are actually requiring that the slope of function at the current iteration here is greater than or equal to a ratio of the prime at 0. All right? So let's present it also in this figure. And recall that we have translated the second condition here. And we are looking for the point alpha k whose slope is between the figure phi prime 0 multiplied by a ratio. Okay? So if we look at this figure, we can find some slope here. So this slope, the tangent part at 0 is actually the phi prime 0. And the slope a little bit horizontal here is the slope of the right-hand side. All right? So the alpha we are looking for must have the slope greater than this slope here. So finally, we can reach the acceptable interval for alpha for the second condition like this. Okay, for the interval here up to here. All right, and another interval is over there. So you can see that for the second condition, we actually rule out the very small size of alpha. Okay, for this alpha, which is very close to 0, we do not select them. So taking the intersection of the two conditions will give us the final acceptable interval of alpha. So any point lying between the two intervals will be candidates of our inexact line search. So we just pick up one of them. They will be our inexact line search step. And then we move forward. Now, you may wonder whether such step length exists or not for any functions. Now, we have this theorem to guarantee that if our parameters C1 and C2 choose as specified here, then we can guarantee that such condition always holds. So, mathematically speaking, that we assume the function to be continuously differentiable, and moreover, we set pk to be a descent direction at current xk, and we require that the function is bounded below along this ray. That means that along this search direction, there must be a minimum value of this function. Otherwise, it is unbounded and it is not a well-posed problem. So the assumptions here are all reasonable. And if the condition C1, C2 satisfies the condition here, then we can guarantee that such step length intervals always exist. So this is a very good and beautiful result, which guarantees that the Wolf condition can always be satisfied. Now, let's make a brief summary about the Wolf conditions. Basically, there are two conditions in the Wolf condition. The first one will guarantee that we have sufficient decrease. The second one will rule out the very small alpha, which may prevent us to slow process. So in the next part, we will discuss more details about other sufficient decrease conditions. So we stop here and see you next time.